This presentation is delivered by the Stanford Center for Professional Development.
Okay, we'll continue with our whirlwind tour of applications in, that are geometric. Last time we started looking at this, the basic linear discrimination problem. By the way, this is very old. This goes into the 40s, this topic. And we asked the question, when can a bunch of points labeled, I've labeled them by changing the symbol from X to Y. So I have binary labels on data in Rn. And the question is, when can they be separated by a hyperplane? This problem goes back to the 40s. Embarrassingly, for many people who worked on this, it was very strange that, in fact, for years, decades, it persisted that people did not know this could be solved by linear programming. I mean, some did always from like day one. Others did not for a very long time. So that's probably even true today, that there are still people who don't know this is the most elementary linear programming. Anyway, so the question was, when can you separate? And we did this trick. This trick you're going to see a bunch of times. You have strict inequalities here. Now, of course, in general, strict inequalities, in many cases, there's no practical distinction between strict and non-strict inequalities, in many cases. In this case, there's a huge difference. If these are non-strict, well, then A equals B equals 0 works always. So here, it's actually the strict is serious. It changes the problem. And the trick here is to notice that these are homogeneous inequalities in A and B. And so they can be, these strict inequalities can be replaced by non-strict inequalities, but with a gap. So 1 and minus 1. Okay? So this is a trick. You need to know it because you're going to see it a bunch of times. It's how to handle strict inequalities that really do matter. Strict inequalities in homogeneous problems.
So what if they were
If they're not homogeneous, well, no, you can't use this trick, that's for sure.
Right.
So you have to argue specially in that case what to do. I mean, in each case-by-case basis. It could be that they're not relevant. I mean, that the difference is not.
Epsilon and just
You can do that, yeah, but you'd have to argue what you're doing is right. Yeah, so that's what you'd have to do. Okay, actually, we'll talk a little bit about when we get to something called phase 1 programming, methods for determining feasibility. So we'll get to that. Okay. Now, you can also, I mean, of course, the set of separating hyperplanes, that is to say the set of A, B, that separate two sets of data, provided they separate. The set of AB is a convex cone. In fact, it's an open polyhedral cone. Okay, so it's an open polyhedral cone. Or if you like, down here in this parameterization, it's a closed cone, but this is enforced a separation. Actually, it's no longer a cone now. It's just a convex set. So then that means if once they separate, you can determine, you can now optimize something about the hyperplane. Probably the most obvious one is to make a hyperplane that sort of has the greatest distance between it and the other ones, or something like that. So one way to say that is to work out the thickest slab that lies between the sets. And the way that works is this. If you have two hyperplanes, for example, the set defined by A transpose Z plus B is 1 and then minus 1. The distance between them is 2 over the norm of A, right? And in fact, in general, A transpose Z plus B is the signed distance to the hyperplane A. It's the signed distance, provided you divide by norm A, to norm of A. It's the signed distance to the hyperplane A transpose Z plus B equals 0. Okay, so that's what that is. So the thickness of this is 2 over the norm of A. So then if you want to maximize the margin here, if you want to maximize this, is the same as minimizing norm A2, and so you end up minimizing norm 1/2 norm A2. The 1/2 is irrelevant, subject to these now inequalities with the 1s and minus 1s. So this is, and this is a QP, and it's a QP in A and B, and it will give you the thickest slab that separates two sets of points. So provided they are separable. Otherwise, this is infeasible if they can't be separated. Now, by the way, geometrically, there's something that should be kind of clear here, and we'll see that it comes out of duality anyway. It's this. If this is the thickest slab, so this problem is basically put a slab in between the two sets of points and then thicken it until you can't thicken it anymore. Well, it turns out turns out it's exactly the same as the following. You calculate the convex hull of the two categories of points like this, like that. And you calculate the minimum distance between these two convex hulls. Okay? Actually, that's an upper bound on this maximum, and in fact, it's equal to, this is just arguing intuitively, the thickness of the maximum slab. So finding the thickest slab between two sets of points, that fits between two sets of points, number one, and number two, finding the smallest distance between the convex hulls of the points. Geometrically, it looks like those should be duals. They should have equal value and so on. And of course, that pops straight out of duality. So roughly speaking, it says that separation problems, maximum separation problems, thickness, when you want to maximize the thicknesses, the duals of these typically are distance problems, distances between convex hulls. Oh, and vice versa. So what this means is when you're solving, for example, a minimum distance problem, the dual will always have an interpretation of somehow putting a thick slab in between things. Oh, and vice versa. Okay. So let's work out how that works. Well, we'll just go back to this problem. The QP here. So we go to this problem here, maximum margin problem, and we're going to work out the dual of this problem. And I won't go through the details now because you can do this on your own. You end up with a Lagrange multiplier lambda and mu. These are the Lagrange multipliers for these inequalities and these. These are lambda and mu for these. And you end up with something that looks like this. You want to maximize 1 transpose lambda plus 1 transpose mu. Some of the lambdas plus some of the mu's subject to this second order cone inequality here, a single one. Then the sum should be equal and they should be positive. Okay. Now, the optimal value of this is equal to the optimal value of this problem. All right. So here I'll change variables to theta I divided by 1 transpose theta. What I have to look at, you have to realize here that lots of things here are homogeneous here. So if I change to theta i's, which is the normalized lambdas and the normalized lambdas, and then gamma i's are normalized mu's, you end up, and then you take t as this variable here. You invert the objective. So instead of we'll minimize 1 over the objective. We'll call that t. Then you end up with minimized t subject to this. And if you look at this carefully, you see exactly what it is. These two say that theta is a probability distribution or a set of weights. Therefore, that is a general point in the convex hull of the xi's. That's a general point in the convex hull of the yi's. This is the difference of the two of them in norm, less than t, and we're minimizing t. So that's the same as minimizing this thing. So it's a distance between the two convex hulls problem. So that's what you get here. So again, I don't expect you to be able to follow any of this. Just the idea is just to see that they are related by duality. Okay. Now I'll mention a couple of things, some of which are, well, both highly hyped and highly useful. We'll get to some of that in a minute. So we can talk about approximate linear separation of non-separable sets. So actually, in many applications, that's quite useful. And if you want to put an application in your mind, let me give you one. You take email, and you take a training set, and you flag it as spam or not. No, there's a person flags it. It's just said that's spam, that's not. And you take the email, and you calculate various features. A feature could be anything. So that's what an expert in this kind of thing would do, is go and work out what the features would be. It might be something, it doesn't even matter what the feature is. It might be the occurrence or not of a term. It might be the frequency of occurrence. It might be the distance between two terms. Could be all sorts of weird stuff. Anyway, but an expert will go analyze the text. Not just text, but also technical things, like maybe where it came from and all that kind of stuff. And you'll take and you'll make a feature vector, and the feature vector might be, let's say, 10,000 long. So then we're back to exactly this thing. So these are now vectors in our 10,000 or something, or roughly. It doesn't matter, 1,000. I mean, that number doesn't matter. It's not 5. There's lots of you have lots of features here. Okay? And what you're hoping is that, in fact, there'd be a hyperplane that would separate the spam from the non-spam. I mean, that would kind of, and then it's great because a new email comes in, you calculate the features rapidly, and simply find out what side of the hyperplane you're on, and that's your prediction as to whether it's spam. So everybody, this is the application. Okay. So in fact, you're not going to get a separating hyperplane. It's essentially impossible. So what's going to happen is a couple are going to be over here, right? That you're just going to miss on some. Real data sets are going to have a couple of points here and a couple points here. You still want to deal with it. You want to come up with something that, I mean, there's lots of ways you can imagine approximate separation. The simplest would be this. In fact, the most natural would be this. I give you two sets of data, and actually you verify by solving the linear discrimination problem that, in fact, they are not separable by hyperplane. That's fine. Then what you want to do is this. Then you might ask, please find me the hyperplane that minimizes the number of misclassifications. I mean, that's just totally obvious that would be the kind of thing you'd want. It makes perfect sense, right? You'd say, I have 30,000 emails, and if in fact I misclassify 0.1%, for example, that's still a bunch of them, that would probably be okay. That would probably be quite good. So but it'd be fine. The idea that you get all 30,000 exactly right is basically generally not possible. Yeah.
Can you use some other shape besides that hyperplane?
Oh, absolutely. We're going to get to that momentarily. Yeah. So you could do. Yeah. Actually, one of the big questions or big pictures or conclusion is, it turns out things you can do in a low dimension space with all sorts of curved separators and things like that. It turns out a very, very good way to do those is to blow them up into a huge dimensional space and do linear separation there. So that's why you hear a lot of people talking about focusing a lot on linear separation. It's generally linear separation in a much larger space, right? Which actually could involve nonlinear stuff. For example, one of the features in this space could be something like the product of the number of occurrence of one word and another. Given our application, I won't say those words, especially because we're being taped right now. But for example, pairs of, so that in that case you think you're doing something that's linear in a high dimension space, but in fact you're really doing something nonlinear because some of the features are products of others or whatever. Okay. I don't know if I answered that question because it got less clear actually. Anyway, well, let's move on. So you want to minimize the number of misclassifications. Well, it turns out that's impossible. That's NP hard to do. Actually, you know what? I'm not entirely certain of that. So let's just say I believe that's hard. That's a hard problem. So it is minimizing number of misclassifications. However, we have a very good heuristic, which you know now, and it's based on these L1 type ideas. So you know that, for example, if you minimize an L1 norm of something, you're typically going to get something that's that's sparse. And so this is an exceedingly good heuristic for minimizing cardinality, which is the number of non-zero elements. So here's what you do. I'm going to put in a little fudge factor. That's UI. Now, if UI is 0, these are going to be positive, by the way. The U and V are positive. If I put in if U is 0, if UI is 0, it means that inequality is satisfied. That means everything's cool. You're on the right side of the hyperplane. You're correctly classified. But I'll put in fudge factors, and they'll be positive, non-negative. If they're 0, it means no fudge factor was needed for that point being on the right side of the actually not hyperplane but slab. That's the right. It's on the right side of the slab if UI is 0 or VI is 0. It's on the right side of the slab. Everybody got it? Now if you minimize the sum of those, what you'd really like to do perhaps is minimize, in fact, something like this: the number of non-zero U's and V's. Because anytime you threw in a fudge factor, it means you failed to meet. It means you failed to meet that, to classify that one correctly. You failed to classify that one correctly, and you need a fudge factor to help you classify it or whatever. So if you minimize the sum like this, and by the way, these could be weighted, but if you minimize, this is going to be a very good heuristic for linear separation of non-separable sets. And indeed, if you solve this problem, it does really well, and you get something that will typically misclassify a small number of points. Is it the minimum number of points? No, we don't know, and probably don't know. By the way, I don't know what this is called in machine learning, this particular one. Does this have like a usually, since they imagine they invented everything, they would have a name for the, somebody in machine learning, is there a name for this one?
Support vector machines.
Isn't this the limit of the support vector machine at one end or something? They probably, I would imagine they'd make up some fancy name for it and then write multiple books on it. But we'll get to that momentarily. It's just this. Okay. Yeah, this is a support vector machine, but it's a limiting case of one. Okay. So, and this is an example where the sets are not separable, and you can see it's done quite a good job of doing this. Of course, all these pictures are silly because the applications of these, I don't have to tell you, are not for separating clouds of points in R2 because your eyeball is excellent at that. Okay. This is for distinguishing binary tagged data in dimensions like 10,000 and up, where your eyeball is not so great. So that's what this is for. Okay, this leads us to the support vector classifier. And here, you make it a bicriterion problem. And the bicriterion problem is this. This is sort of the fudge factor here. But in fact, here you can also trade off the width of this slab. And if you do that, you end up with something like this. This is one version of what's called support vector. Oh, and this is just so pedantic. It's called SVM by people in machine learning and things. Anyway, it's remarkable. So, I mean, it's nothing. It's just, it's two things. This is basically the inverse width. This is the inverse width of, it's 2 times the inverse width of the separating slab. This is an extremely well-known, totally elementary heuristic for making this sparse, meaning please misclassify few. And you get this, which is nothing but a QP. All right. That didn't stop people from writing like multiple books, all of which are more or less incomprehensible. Many of them are completely incomprehensible. But anyway, so it's called a support vector machine. Don't you like that? A support vector machine. It's great, isn't it? It's kind of like, okay. So it makes it sound fancy and yeah, so on. Okay, so that's it. And here is, I think, the same data set. It is indeed, here's the same data set. Here, we put, let's see what we did. We put less weight on gamma here. And what that meant is we spent more effort making A small. You make A small, 2 over norm A is the width. So this thing opened up like that, and I got this one. Actually, it's a bit different. Let's see. I don't know if I can overlay them, but well, I can't see it, but maybe you can if I go from there to there. Yeah, it twisted around a little bit or something like that, but okay. Now, even though it's sort of hyped, I have to say the following. These things work unbelievably well. So, in fact, things like, you know, most spam filters and things like that. Of course, you have to have the right features. But generally speaking, these things work like really, really well. So, which kind of makes sense. Things that are overhyped and then don't deliver kind of go away. This is not going away. So, I assure you of that. So, okay. Somebody asked about linear versus nonlinear discrimination. You can do anything. I mean, you can easily separate things by a nonlinear function. For example, you might linearly you might have a function which is itself a you would consider a linear a subspace, in fact, of functions. Now that's exactly what we did here. So far, we do linear classification, which you might really call affine classification. The class of functions you look at are affine. Here, they could be anything you like. It wouldn't really matter. What matters is the following, is that the function family that you look at is linear in the parameters. That's all that matters, in fact. Then everything works. You can do, discrimination with anything you like. They could be, polynomials. They could be all sorts of crazy things. Well, I mean, for example, you could make them Gaussians and things like that, and you could do discrimination that way. And Gaussians parameterized with different widths and different positions, and you could get quite fancy and do separation that way. But as far as we're concerned, they're all very simple. The base problem is always a linear program. So, period. And just as an example to see what you can do, suppose you said quadratic discrimination. That basically says you parameterize f by P, Q, and R. And so you're searching a solution of these inequalities. Now the variables here are P, Q, and R. So in fact, these inequalities in P, Q, and R are what? They're what? What kind of inequality is that in P, Q, and R? It's linear. It's just linear. So this is nothing but a set of linear inequalities in P, Q, and R here. But obviously now I can add other constraints. If I make P positive definite or something like that, then in fact it means that this one will be, well, negative definite. Then it means that this one is actually an ellipsoid. So I could add the constraint, please make me an ellipsoid that covers my data and doesn't contain as many of these. And of course, once you get the basic idea, we could even make a, let's see, how would you call that? A support ellipsoid machine, SEM, the new rage in machine learning. You could say, well, what if you find me an ellipsoid that trades off, size of the ellipsoid versus number of misclassified or blah blah blah, and we could easily make this up this way. It'd be extremely simple to do, right? To do that. And then you get approximate ellipsoidal separation and things like that. But let's just try a few. I'll try a few things on you and see what you think. What if I said, suppose the dimension is huge, and I only want to look at, for example, P's that are banded with bandwidth 5. Will that work? Can I solve separation by a P which is banded with a width of 5? Sure. It's just it's a subspace. That's no problem, right? So those kinds of things will work. Okay. Here's another example where there's a bunch of data here, and this is separation by a 4th degree polynomial. For example, there's no 3rd degree polynomial that separates them. So you could solve by quasi-convex optimization clearly the problem if someone says, do you find the minimum degree polynomial to separate these sets? Actually, more generally, if I set a basis elements but ordered, so I gave you an ordered set of basis elements like F1, F2, F3, and so on, and then I said, find the minimum number of these taken in order that separate the points, that's quasi-convex. Because you solve an LP feasibility problem with some number of them, and then you know whether you can separate with that number of basis elements or not. Okay, so that's the idea. Okay, we'll move on and look at one last sort of topic in a family of problems in geometric optimization problems. And these are placement and facility locations. Again, there's tons of varieties on these things. There's whole books on these. So the idea here is just to give you the flavor of them. So placement and facility location problems generally look like this. You have a bunch of points or coordinates. Now, often these are in R2. Sometimes they're in R3. But they're often not in higher dimensions, but there's no reason they couldn't be. So they could be in R2. They could be in R3. They could be in R4, which would be something like space-time or something like that. Then what happens is this. You have a bunch of points. We'll just make it R2. A bunch of points are given, and the others are variables. So for example, what happens is you're given, these are I'll make these fixed, and then the variables are these. So you can think of these. There's many names for these. These are sometimes called anchors, depending on the application, because they're the ones that are fixed and don't move. And then these are sort of the free points. They move around. Okay? Oh, the other name for these in circuits is pins, for example, or something like that. Fixed cells or pins or something like that. And what happens is for each pair of points here, you'd have a cost function. It's a function of the pair of distance. In fact, usually it's a function of a norm of the difference. But it could just be a function of the pair. And I give you some examples here. Let's do circuits, for example. So in circuits, we're placing cells here. And what I will do is this. These are fixed. These are maybe these are external pins or other blocks or whatever whose position is fixed. You're doing placement. And these are cells that can move around. And I have a net list, meaning I have connections in between. A bunch of these things that look like this, something like that. And in fact, each of these might have a weight on the edge, which would be the number of wires that connect one cell to another. Okay? And the absence of an edge means there's no wires connecting it or something like that. So for example, there's no wires directly connecting this cell and this one, for example. And now your goal is to position these to minimize, for example, the total wire length. That's a very common problem. And in fact, the wire length would typically be done, I mean, if you care about this, it would be done in an L1 norm because you do vertical, horizontal routing of wires in a circuit, for example. And you know, there's all sorts of things that make this more complicated and so on. This could be sort of a radio relay network or something like that. And the distance between two nodes could be the following. The cost could be the following. It could be the power required to establish that wireless link. Right? And that would be, for example, a function of the distance, for example. And in that case, I'd say, please move my mobile forwarding stations in such a way that the total power used by the network is minimized, for example. I mean, I'm just making up examples. They just go on and on and on like this. And you could say, I have a distribution of a commodity. These are the warehouses. Each of these lengths could have each of these things could have a weight, which is the amount of traffic that goes between these two places. And you could ask to put this in such a way that the total amount of freight times miles is minimized, just for example. But okay, so that's a typical placement problem. Okay, now these, of course, are all convex. These. Now, by the way, the minute you start doing placement, there's all sorts of other stuff that immediately pushes it out of the convex realm. And I just mentioned a few of those just for fun. One is if you're doing placement in circuits, there's another rather important constraint. That is that cells should not sit on top of each other. So that's non-overlap constraint, and that's not convex by any, not even remotely. Because you're placing cells. So that's one problem. And of course, in all the other ones, they're silly. It turns out, for example, if you have to go, if you want to look at the power required to transmit from 2 points, it might not be just a function of the distance. It might depend on the terrain and things like that. Then this gets then it's clearly, again, non-convex and so on. But first cuts are typically convex like this. So here's just a simple example. We're going to minimize a function of a 2 norm of the distance of the pairs. We have 6 free points, and I think the anchor points are these around here. And there's 27 links here, and here are the 6 free points. So if you minimize the sum of the norms, you get this picture here. If you minimize the sum of the squares of the norms, you get this. And you can actually see what's happened here. Oh, by the way, you know, you're not going to get stupid with these things. You're not going to get stupid placements, right? For example, this node is not going to be, no one is going to place themselves outside the convex hull of the anchors, for example, right? Because moving it just to the boundary will decrease the distance. You're not going to get this point sort of way over there, right? Oh, I should mention one other application of these things. One is just drawing or visualization. So that's a perfectly good example. So for example, I might have, drawing or visualization would go like, you know, I'd have a bunch of points. And I would have some measure of sort of a similarity. And you want similar things. You want to plot this on a screen or on a piece of paper. And you want similar things to be close to each other. So what I have is a dissimilarity measure or something like that. And so I want to place the points so that similar things are close. And dissimilar things are far away, just for example. And this is the kind of thing that would do that. It would cluster similar things and so on. Okay, so here you can see what's happened is here you have a lot of, in fact, I should mention something here. If you minimize the sum of these norms, that is just like an L1 type thing. So what's going to happen is a bunch of these are going to be equal. So if I have 6 free points, let's see, did it actually happen? 1, 2, 3, 4, 5, 6. Okay, so I believe, but I can't see closely enough here. My guess is that 2 of those, at least 1 point is sitting exactly on top of another. They cluster. So if you minimize sums of norms, they will cluster. It's just like an L1 type problem. They'll cluster here. Okay? And you will have some long ones. And if you look at the histogram of interconnection lengths, you'll see you have some wires that are as long as, or lengths that are as long as 1.5 and so on. and you have, let's see, well, so we may have one that's 0. There's at least one that's very small. Might be actually exactly 0. My guess is it's exactly 0. When you go to squares, what happens is these long lengths irritate you. Well, they irritate you squared compared to just linear irritation. And so this spreads out so that the longer lengths are shorter, which is better. And you have bigger distances in the middle, like this. By the way, the name for this is quadratic placement. This is called quadratic placement, used in a couple different fields. And then you could do something like you'd have the 4th power, and that will spread it out even more. Let me ask you a couple questions here. We'll do it this way. What if h was this? It's you get a free ride for 0 to 0.3, and then it grows linearly. What do you think the placement's going to look like?
It's going to be a lot at 0.3.
Yeah. It says basically distance is free up to 0.3. So what's going to happen is when you solve this, they're actually going to spread apart. And a lot of them are going to be just exactly 0.3 away from each other, right? Some will be longer because they may have to be. Some will be shorter because it doesn't matter. But a lot of them will be about 0.3 away from each other. So that's it. That's what will happen here. So all the same ideas, once you start understanding about how to construct these functions, everything comes into play. I mean, I could even do this. I could then make this go to plus infinity at 0.5. And then, of course, no wire length will be less than 0.5. It might be infeasible, but if possible, it will arrange that no wire length is less than, if these are wires, no wire length is more than 0.5, for example. Okay. That finishes up this whirlwind tour. You should be reading the book as well, because it goes into much more detail on these and the variations and things like that. Because, first of all, I'm going fast, and so anyway, you should be looking at the book. Okay, we're actually going to start that actually sort of finishes one section of the class, although it's not really, because it'll just go on forever now. That's our whirlwind tour of applications, and we're just going to we'll just be doing applications, as I said, from now on, no exceptions. Until and through the final, we'll just do lots of applications. But we're going to start a new section of the course, and it's actually on the algorithms. So how do you solve these things? About how, I don't know, the codes you've been using, how do they work? What do they do? And we'll go through all of that. You'll end up knowing not stuff at the ultra high end, but actually well enough to implement things that work like shockingly well. And in some applications work better than sort of generic custom stuff. We're also going to cover, actually the stuff we're going to work on, we're going to do today, we're going to start today, is extremely useful. Basically for anybody taking this class should know the material here. Probably some people do. Actually, how many people have actually had a class on like numerical linear algebra and so on or something like that? So just a handful. Okay, so everyone should know this material. Just period, end of story. It doesn't matter if you're the most committed theorist. Makes absolutely no difference. There's no excuse not to know this material. So that's my view of it. And actually, it's just a few things will get you very far. That's the problem. If you get books or take a whole course on it, it's just too much stuff and too much detail. And it's so much stuff and so much detail that by the end you've been so pounded with all this material that in the end you can't even remember what the main points were. So, but we'll do it so lightly and at such a high level that you'll have no option but to realize what the main points are, because we're not going into any others, and we'll barely go into them. So, okay, so this is and let me also just put this in perspective. You will know, actually, it won't take very long. You will know how to, for example, solve a second order cone program or an SDP. I don't know, a couple weeks. That's all. You'll implement one absolutely from scratch, and it'll work. And it'll work actually like really well. Okay, so and it's not a big deal. We're talking like 30 lines of code. It's just nothing. It won't be competitive with something that's got thousands and thousands of person hours of development in it. But you'd be shocked at how well it's going to work. So let me say a little bit about how it works. Oh, by the way, I should say my position also on all this material. So So when I talk to a lot of people, so a lot of people who use optimization are sort of very naive about it. And everyone is fascinated by this. It's just all the algorithm. That's all they care about. And so you mention something, and I'll go somewhere. It's kind of obnoxious, but I'll say something like, that's an SOCP. And they'd say, oh yeah, oh great, sure, what's that? But then they immediately focus in on like, how do you solve an SOCP? In which case and I think sort of the correct response to how do you solve an SOCP is, it's none of your business. It's technology. It's just not your business. SOCPs can be solved very well. There's a thriving community of people who do it. There's lots of algorithms worked out, tons of papers on it, open source software. There's also commercial software if you prefer to pay for it. I mean, so it's sort of not, but everyone just wants to worry about how you do it. Now, of course, if you solve giant problems, that might be necessary. Obviously, right? If you solve, so this is why I don't recommend you go into either machine learning or image processing or medical imaging. These are just, if you're already in one of these fields, sorry. It's too late. Because it means you are going to have to know how to write your own things, because you can't just use generic stuff to solve problems with 10 million variables. If you're in another field, good, stay there with a modest number of variables, like 10,000, maybe a couple 100,000, something like that, and also avoid fields with real-time constraints. So any field where someone could say to you, "That's great, but that's way not fast enough," then again you should avoid that field. Again, this is only if you have not chosen a field to go into. But all right. Where am I going with this? I have no idea. Okay. No, I know. I just remembered where I was going. Yes, of course. Oh, so I want to say that basically what I want to say is this whole section of the class on numerical stuff, it's good to know it, but remember, most people will focus on this. If you take a class like this at some other institutions that I won't name, well, I would name it, but I'm not going to, you will find the entire class, basically from the beginning to the end, is sort of on algorithms. I mean, this would be weird. This would be like taking an entire class on like TCP/IP, right? I mean, you can do it, and somebody has to do it, right? Otherwise, the rest of us can't use it. But there's just something weird about thinking that's what's important to teach about this material. What's important to teach about it is actually the applications and the modeling and all that kind of stuff. This is way secondary. But having said that, we're going to now launch into it. And let me say what the big picture. So the big picture is this. Let's say you're going to solve, we're going to solve nonlinear constrained, inequality constrained problems. Okay, we're going to build our way there. And the way that's going to work is this. We're going to build it up by we're going to solve each more sophisticated layer by solving a sequence of ones at the next layer. This is just I'm going to give you the big picture right now. This is how it's going to work. Let's just take an LP. I mean, okay, so let's just take, here's an LP. And the way we're going to solve an LP is you're going to solve a sequence of of nonlinear, but smooth minimization problems. That's what you're going to do. That's how we're going to solve an LP. Is you're going to solve 20 smooth nonlinear minimization problems with no inequality constraints. That's what you're going to do. Okay? How are you going to solve these? You're going to solve each of these by solving a sequence of, in fact, quadratic minimization problems. Okay? That's how you're going to solve these. This is going to be Newton's method, by the way. The name for this is an interior point method. Then this is Newton's method that converts minimizing a general nonlinear convex function to one where you solve a quadratic minimization. Now, by the way, quadratic minimization is very interesting because if I ask you to minimize a convex quadratic subject to an equality constraint, the solution involves solving linear equations. So this is basically, that's a sequence of linear equations. Okay? So what it basically says is the following. When you solve an LP, yeah, you'll do about 20 of these or something like that. And it doesn't really, let's see. Is that about right? Yeah, even less, sorry. You'll do like, 10 of these. Each of these you'll do 5 of these. And so the point is that what will really happen is if someone profiles your LP solver code, it will discover that it's doing basically only one thing. It's solving linear equations, and it's doing so 50 times. I'm just giving you the big picture. But the point is that the whole foundation rests on linear equations. Oh, by the way, we could go lower, because linear equations rests on, multiplication and this sort of stuff, and you can go down then. And then we can actually talk about floating point calculations and blah, blah, blah. So you could get I mean, we could keep going, but we'll just stop right here. Okay, so this is why solving linear equations is important. So, all right. So, we'll start by talking about sort of matrix structure and algorithm complexity. So, how does this work? We'll just look at just AX equals B with a square matrix. Okay? Now, for general methods, the cost of solving AX equals B grows like n cubed. And that's just that's approximate for some reasons I'll say in a minute. And just for fun, I mean, last night I typed into my laptop, and so how long? By the way, n cubed when n is 1,000, it's not a small number. It's 10 to the 9. Roughly, it's on the order 10 to the 9 floating point operations go down. How long do you think it took for me to solve AX equals B? This is on my laptop, which is 2 years old. Last night.
A few seconds.
What?
A few seconds.
Okay, that's a good number. Any other guesses? Yeah, I mean, actually, order of magnitude, you're in the ballpark. That's a lot, right? 1,000 cubed is a lot. Okay, so the answer is half a second. Okay. So that means on a modern machine right now, it'd be substantially less. Okay. So I mean, you want to get some rough idea. I mean, that's actually why all of this is possible, is because basically computers right now are way I mean, amazingly fast. Okay. So that's about half a second. By the way, for fun, I went from 1,000 to 3,000. It should have gone up by a factor of 27. Is that right? No, 8? Sorry. Yes, no, 3. I did 3. I went 1,000 to 3,000 for fun. Should have gone up by a factor of 27. It actually went up only by a factor of 20. But roughly, that was it. And I dropped it down to 100. By the way, what's the prediction? If n equals 1,000, took 0.5 seconds on my laptop, how about n equals 100? By the way, the number you're about to work out is it's a very important number, actually, and it's something that is not appreciated at all. I mean, like throughout the world. So what's the number? I mean, if it scales like n cubed, what's the number? What is it? Yeah, it's 500 microseconds. Okay? Now, I think we should probably have like a moment of silence to reflect on what this means. This is unbelievable what this means. That solving a set of 100 linear equations with 100 variables. Just the data, there's 10,000 data points. Did I get that right? I mean, that's just to describe the matrix, okay? This is not a small thing. Okay? That goes down in 500 microseconds. That's predicted. And the actual number, by the way, was about, I guess, a millisecond or something. Okay? So these numbers are just amazing. And this is with all the stupid MATLAB overhead and all that kind of stuff. So this is, by the way, MATLAB, of course, has nothing whatsoever to do with the actual algorithms that run. The algorithms that actually run in MATLAB that do all the numerics are open source public domain. It's called LAPACK. So don't ever confuse the two. Okay, so these are just amazing numbers, what they are. So it's just worth, I mean, I know everyone knows these things, or actually I know most people don't, by the way. If I go around and hang out with other professors who do stuff that involves, like, you'd be shocked at the numbers people would guess like this. I mean, they're well-respected people whom I won't name. But I've had people guess recently things like minutes for this. So minutes for 1,000, right? So, of course, it's not their fault. If you kind of don't pay any attention and a decade goes by, Moore's law propagated forward by 1 decade, I'm sure I've done that too. I could say, oh boy, you could probably do that in about a minute. And then, anyway, you keep saying that a couple of classes and you're wrong pretty quickly. So, okay, all right. Back to this. Okay, that's n cubed. Now here's the part that's important. I mean, this is basically you should get rough idea of, everyone should know these numbers. There's no excuse not to. It's silly. Now here's the really cool part, and here's actually what we're going to cover in the next lecture. And this is very important to know, and makes these numbers even more shocking, way more shocking. If A is structured, like banded, sparse, couplettes, and we're going to see a lot of other types, some that people would not recognize, most people. Okay, in that case, it's way, way faster. Now, for example, let's just do a quick example. Suppose A is tridiagonal. Anybody know? Someone who's done numerical computing will know how fast you can solve a tridiagonal system. How fast?
Substitution?
It's actually n.
Oh, yeah.
It's n if it's banded. It's n. So what that means is, for example, solving a million equations with a million unknowns with a banded matrix, it's like that. Okay? So, I mean, these are not secrets or anything. Okay? The people who do this all the time know it. Actually, but other people should know it. You should know it. There's no reason for you not to know this kind of stuff. Okay? Actually, what'll really matter is then we'll make all the neural connections between the application and these things. And then you'll look at something like an optimal control problem or signal processing. You'll look at it. All the neural connections will go through, and you can say, that problem I can solve with a million variables. That signal processing problem. That image restoration problem, I can solve that with a lot of variables because blah, 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 banded or such and such. So we'll get to all these things. Okay, so how do you estimate an algorithm for solving AX equals B? Well, this is really from the 60s, so it's a bit sort of behind, but it's still a useful concept. Although no, you shouldn't take it too carelessly. Too carefully. It's a flop count. So flop count is something like a floating point operation. It means it's something like this. It depends how you do the accounting, and in fact, it doesn't really matter anymore because it's not that accurate. But it basically means something like an addition, subtraction. It's something like an addition, a subtraction, a multiplication, and it also sometimes they throw in something like they amortize a little bit of indexing or something like that. So it's just a very crude number. By the way, it was not a crude number in the 60s and 70s and 80s, maybe early 80s. It was not a crude number because a floating point operation would actually often be like shipped off to a separate chip or something like that. I mean, it was like a big deal to do a floating point operation. So counting floating point operations then made a lot of sense and actually would give you a pretty accurate idea of how long something would run. These days, of course, it's really close to meaningless. I mean, it's kind of silly. What matters now, obviously, is things like cache misses, locality of reference in memory. Things are deeply pipelined. All sorts of stuff is going down at the same time. So floating point. I mean, you can write down two algorithms, analyze the number of floating point operations, and they can run, let's say, 1,000 times off in speed. This, by the way, hints that counting floating point operations is not such a super good measure anymore, that they could be off by a factor of 1,000. Still, it's roughly useful. But it means don't take a number seriously. If someone walks up to you on the street and says, I have a new algorithm, and it's, the usual one is like 1/3 n cubed. Mine is like 0.2 n cubed. Then you can just laugh and walk away or something because it's so far off. Below the threshold of significance, it doesn't matter. Okay. So here's what people do. Again, it's from the 60s, and it's not quite right, but it's it's still a useful idea. What you do is you count up roughly the number of operations required to do something like solve AX equals B. And that will generally, in the problems we're interested in, be a polynomial function of the problem dimensions. You may be estimating stuff. That's fine. And you simplify by keeping only the leading terms. So you'd say that's an n cubed algorithm, or that's an n to the 2.5 algorithm, or it's n, or linear it's just order n. Okay, so as I said, it's not an accurate predictor of computation on modern computers, although, by the way, that's what I was doing here. Later, I'll actually tell you exactly what was happening in these two cases. And actually, the fact that I was predicting within a factor of 2 or 3 is pretty good. Well, actually, only because it was all optimized, but we'll get to that later. But it's still useful as a rough estimate of complexity. Okay, so some of this is pretty basic, and I should mention something about this. I think everyone should know about it. We're not going to get into this, but it's just to give you a glimpse below where we're going to go in the class at the lower level stuff. Actually, all of this, the linear algebra we're talking about now, is done in something called LAPACK. Which is linear algebra package, which is open source software. It's among the most debugged software anywhere in the world because it's used by lots and lots and lots of smart people. It's written by very smart people, totally open source, and it's basically it's everything you do. If you use MATLAB, Octave, anything else, it's going to use LAPACK. We'll get into some others. And I presume that's true of R as well, but I don't know. Do you know? Yeah. There we go. So it's R as well. Okay, so this is what, and basically below LAPACK, there's something even lower called BLAS. Again, this is just, it's not part of this class, but it's just if you want to look below the level we're going to go, these things are very good to know about. BLAS is basic linear algebra subroutines. Okay? And they distinguish BLAS level 1, 2, and 3. So BLAS 1, BLAS 2, BLAS 3. You'll hear things like this. If you don't hear things like this, you're probably not hanging out with the right people, by the way. Just, so if most of your friends are talking about square root n log n complexity, you should at least get some friends that talk about these things, just to kind of get a more balanced view of the world. Okay, so BLAS level 1 is generally like things like vector-vector operations and things like that. So these are separated logically this way. So these are actually BLAS level 1. So here this would be things like calculating the inner product. Well, how many flops does that take? Well, you have to multiply the pairs and then add them all up. And it's 2n minus 1. And people just say 2n. Or they just say n. And by the way, some people count flops a factor of 2 off. So some people say a flop is actually kind of a multiplication and an addition, plus a little bit of indexing. So basically, the usage of the word flop is inconsistent by a factor of 2 immediately. Which is fine, because it doesn't predict anything more than a factor of 2 anyway nowadays. So you would just say this is order, you'd just say this is n. If you add 2 vectors, this is silly, it's n flops. What you want to start thinking about here is what happens when there's structure. There's not much structure you can have in a vector. Well, there is one. You can have a sparse vector. If you had a sparse vector, then how would you calculate the inner product between 2? Suppose my vectors are each 100 million long, but each of them only has 1,000 non-zeros. Stored in some reasonable data structure, right? Simple. Let's just make it simple. We're not going to do an exotic one. How would you calculate the inner product between 2? You wouldn't ask each one in turn, please can I have, xi, please can I have yi, multiply the numbers, and then plus equals that onto your accumulator or whatever, right? You would not do that. What would you do?
Where they are the same?
Yeah, you find the common ones, and so basically it would be blazing fast. So this is an example, a stupid, simple example of where structure comes to make not a small, we're not talking about small increases here, right? We're talking about dramatic increases in efficiency, right?
Like, how does knowing something structured help you in actually doing these computations? Doesn't it take some work to actually figure out what's zero?
That's an excellent question. Okay, and we're going to get to exactly that question. Excellent. If I don't answer it today sensibly, I'll answer it on Thursday. The question was, how does knowing something structured help? Okay, so I'll tell you the answer right now, roughly. May not make much sense. It's this. Some structure can be, in some cases, automatically handled for you. Some types of sparsity patterns and things like that will be automatically recognized, depending on the software system you're using. If you're writing sort of high-level stuff, like in Python or MATLAB, some structure will be recognized, other structure won't be, okay? And that's the one that'll be the interesting part. If you're writing actually production code or stuff that actually work for something large, knowing the structure is there helps you this way, because now guess who's going to write the code for it? You. So we'll get to that. Now the low-level stuff you don't have to do. A lot of the structures there will already be things that can do. Actually, sparse is not one of them. There's no absolute standard now. But for a lot of other things, there will be. There's actually code low level, so there you should know about it. All right, let's move on. Matrix vector multiply. Here, if A is dense, or you treat it as dense, then you want to do a matrix vector multiply. You just work out how many. It's basically 2mn flops, because you basically calculate an inner product with each row of A and X. And that's what it is. It's that. If A is sparse, if a matrix is sparse and it's got around capital N non-zero elements, then that's all you're going to have to multiply by here, because you're going to just calculate those, and that gives you this. Now, if A is given a different data structure, like for example, suppose A is given as a low-rank factorization. So suppose A is, it doesn't matter. A could be like a million by million, but I give it as a rank 10 factorization. And note that would allow me to store A, because there's no way you're storing a million by million dense matrix anyway. You can't do it. But I could store A as 2 million by 10 matrices. That's nothing. And here, the key is to store it as this and to multiply A by X by first calculating V transpose X, which gives you 10 numbers, and then forming U times X, which gives you 1,000,000. And that's fast. That's going to be 2P times M. In this case, if that was 1,000,000, this would be something like 10, on the order of 10, 20 million flops, which, as you know now, goes down way, way fast, as opposed to something that just wouldn't work even remotely. By the way, to go back to your question about knowing structure and so on, there is no system in the world that will recognize for you low-rank structure. So if you anywhere in your code write something equals U times V, like this, there's no system right now that would check and say, oh, silly guy, that's actually rank 10. Anyway, it wouldn't work anyway here, because if you formed U times V where they're million by million, it's all over anyway. It's just nothing. It'll stop when there's no more virtual memory left or something like it. It'll just stop at some point. So low rank structure is an example of structure that is not discoverable. Sparsity is sort of discoverable, and you have generic methods that do it. So, okay. Matrix product, that's C equals AB. Now here, the number is approximately, MPN. So it's the product of the sizes like this. That's what it is if it's large. Now, if A or B is sparse, it can be much, much less. By the way, this is it's not at all obvious. Actually, when you have sparse matrices, if you really want to work out good data structures for storing and manipulating sparse matrices, it's quite complicated. And a lot of the data structures you think of immediately are not that great. I mean, the most obvious one a person might think of would be a key-val pair, triplets, well, key-val pairs, and it would look like this. That's how you might imagine is a whole bunch of things like this. That'd be key and then val paired, something like that. That's how you might imagine. That's probably the most natural for a person. Turns out that's a very poor data structure for this. And so the ones that are actually used vary from simple but sort of practical. That would be, you'll hear column compressed, what's the last term on that? Column compressed format or something like that. So you get column compressed format, and it's just some weird data structure. It's kind of like a data structure that's a cross between simple and close enough to machines that you get something fast. But then you get all sorts of exotic data structures for storing sparse matrices, which I won't go into. But if you look at this area, you'd find out about them. Okay, actually, this is a good time for me to point something out about this, because it's a very good thing to know. Let's take matrix multiply. Okay, everybody here knows how to write a code for this, like in C. It's nothing, right? All you do is you take A and you B, any language, it doesn't matter. You take A and you B, and you're going to calculate Cij, or let's do this. You say for I equals 1 to n, for k equals, let's make them all n by n because I don't really care. For I equals 1 to n, and for k equals 1 to n, you're going to calculate Cik. And so you simply walk across A, down B, and add these up. So you get like 6, 8 lines of C, something like, everyone could write that right here, right? And you compile it, and you will have a little function called matmult A comma B. Everybody got it? And it will multiply matrices, Well, it's not exactly a sophisticated computation you're carrying out, right? Okay, so now let me ask this. I know I mentioned this in 263 if you took that class, but let me ask you this. You imagine that it doesn't look like there's a whole lot of room for creativity in the matmult thing. I mean, if you were like scanning some code and wanted to know where to optimize something, you probably wouldn't take matmult and the ensuing 5 lines of C, 2 of which are comments, as something that you'd optimize. I mean, does this sound reasonable to everybody? Yeah. So here's the weird part. If you use the LAPACK version of this, it could easily be 10 times faster than yours and could definitely be 100 times faster. Now, by the way, there's no structure being exploited. Total number of flops that go down in each case, identical. It's whatever it is. If it's 2 n by n matrices, it's like n cubed or something. Okay? Everybody, you have to let this sink in what I just said, because it's ridiculous. Everybody see what I'm saying? Now I'm going to ask you this. This is just a fun question. Why? What does LAPACK do that you didn't in your 6-line C program? It blocks. Okay, so in fact what LAPACK did was it will actually break this up into blocks and then multiply blocks at the same time. Why does that work? Because some blocks are optimized, the size is optimized perfectly to do register-register calculations. Okay? Then the next block is optimized for your level 1 cache and so on and so forth. Okay? By the way, if you don't know what I'm talking about, that's fine. But whether you know what I'm talking about or not, you must know the following, that when you get into numerical computing, there's things that just look like, if you don't know about this, and someone tells you that there's a good and a bad version of writing something that multiplies two matrices, right? It's just not obvious that it even makes any sense, but it's absolutely the case on modern computers, so that's how it works. So, okay. And I'll say more about that later, but this is the first thing that, maybe if you don't know about this field, this is not obvious. Okay. So let's talk about linear equations that are easy to solve. We'll start there. So, well, look, if A is diagonal, it's very easy to solve AX equals B because you just simply divide by the diagonal entry. So that's nothing. And that takes n flops, okay? If a matrix is lower triangular, that's the first one that's not totally obvious. It looks like this, A11, A21, A22, A31, A32, A33. This thing times, x1, x2, x3 equals, B1, B2, B3, like that, okay? How do you solve it? Well, you first go after x1, because this first equation is A11, x1 equals B1. You divide and get it. Once you know x1, you go to the second line, and it says A21, x1, but you just calculated x1. So you substitute it back in there. Okay, so you actually calculate x1 and then you substitute it forward. This is called the forward substitution algorithm. Okay? And what happens in this case is you successively calculate x1, x2, x3, x4. Once you've gotten down to here and you know everybody above here, it means that you know these guys, you multiply by these, and that's just a number, and it goes on the other side and you divide. So it's very simple. By the way, this thing works for block methods as well. These could be, the A's could be blocks, block lower triangular you can also do. Now I can't use this code wouldn't work, but had I written this the right way as A22 inverse here, then my notation would have overloaded correctly in the block case. Okay? So this is, now if you do this, if it's dense, this takes n squared flops this takes n squared flops here to work, because you work out. It's basically, it's how these work. It takes like, 1 flop, then it takes 3, then 5, then 7, and you add those numbers up and you get n squared. Okay? Because you keep adding. Anyway, I'm sure you know how that works. Okay. By the way, if A is sparse, then this forward substitution basically depends on the number of non-zeros in A. Very, very fast. Okay, if A is sparse. So forward substitution becomes fast. If a matrix is upper triangular, you just solve from the last element up, and that's called backward substitution. Okay. Well, there's lots of others. I mean, you can have an orthogonal matrix. If a matrix is orthogonal, then basically the inverse is the transpose. So you multiply by the transpose. And that's for general A. But in fact, often an orthogonal matrix is stored with a different data structure. One common data structure, in fact, would be a product, just for example, of matrices of this form. That's a very common data structure used to describe an orthogonal matrix. And this here, you have norm u equals 1. If you do that, then to multiply A transpose here by a vector, by the way, that's a perfect example of a matrix vector multiply. This matrix, of course, in general is dense, right? So if you form this outer product, it's going to spray non-zeros over the whole matrix, right? So that'll be a dense matrix, and a matrix vector multiply will cost you order n squared. I think I got that right. Okay? But here, if you exploit the fact that this is identity plus rank 1, and calculate it this way, when you're past a vector, you first multiply by you calculate an inner product, then multiply by u, and then subtract that from your original one. It's an order n. So matrix vector multiply for this structure of matrix has gone down from n squared to n. Here. Okay. Another example would be a permutation matrix, and it's actually, this is a great one. It's interesting. If you have a permutation matrix, so in the traditional 1960s term, you'd say there's no flops because you don't do any floating point calculus. You're just doing index tricking. The funny part is actually nowadays this is exactly what you don't want. This is, I mean, if you're actually calculating, it's like data movement and stuff like that. So this, in modern times, this would be a relatively expensive operation, and it runs up according to the metric we're using, 0 bill is permutation. So, okay. Now I can tell you about the big picture of how you solve AX equals B. Well, the general scheme is this. You take the matrix A and you factor it as a product of simple matrices. These could be diagonal permutations, orthogonal, upper triangular, lower triangular, block, upper triangular, these kinds of things. So you factor it this way. And then you compute A inverse B as the product of these inverses in reverse order, like that. Okay? You multiply by B. So you actually, let me just put the parentheses in the right place. You do this, then that, and so on, up to that. Okay? So you factor, and then you solve actually from the first one backwards, is what you do. Something, I think I have it right. Something like that. That's how you do it. Because each of these operations you can do fast. So that's how you do this. Okay. So, and in each case by the way, people write things like A inverse B because that's what you write in math. But often when people say, compute A inverse B, that's just sort of understood to mean not that you actually compute A inverse and multiply it by A. It means that you call a method which is something like solve A comma B. But it's just weird to write that, so people write A inverse B, and it's simply known that you wouldn't actually compute A. You wouldn't take the pseudocode literally and actually form A inverse multiplied by B. Okay, so, okay. Now actually, once you know this, you already know something that is not obvious. Well, you already know one other thing that's not obvious, that basically LAPACK will beat the hell out of your 6-line C program, or can. That's another thing that's, I believe, not obvious. To multiply two matrices. To do something as stupid as multiply two matrices, LAPACK, properly configured and optimized, will beat you like by a wide, possibly very wide margin. Okay, second thing that's not obvious, again, if you don't know this material, it has huge consequences, and it's this, and it's very cool. It's this. Suppose you want to solve a set of equations with the same matrix, but multiple right-hand sides. Okay? That comes up like all over the place. Suppose, for example, I don't know, AX equals B really represents solving a set of circuit equations. B is a set of current sources injected into a circuit. X is the set of potentials at the nodes in the circuit. So that's what AX equals B means. All right. In that case, it says, suppose you want to, and basically solving AX equals B is doing a circuit simulator. Basically says, inject these currents. If I inject these currents in the circuit, please tell me what the potentials will be at the nodes. That's what solving AX equals B is. It's a sim. Now, once you know about factor solve methods, you know the following. If you have multiple sims, so you're saying, you know what, I would like to know what's the potential distribution in the circuit with this current excitation, and also this one, and also this one, and that one too. Okay? The naive way is simply to call the sim code 4 times. Okay? But in fact, that's silly, because the factorization on the matrix only needs to be done once. So once you have actually factored a matrix into easily solved systems, that is amortized across all the solves you do. And so here's just a totally weird thing. You can go and do this in MATLAB, although just because it's using LAPACK. You can do the most amazing thing. You can just go and you can time that. A has to be reasonable, or otherwise it's too fast and interpreted overhead. Anyway, so you could time that, and then you could time this. What's the time difference going to be for dense matrices? I have to tell you that the factor costs n cubed, and the backsolve you now know is n squared. What's the time difference between these two going to be? What's it going to do? It will actually do the right thing here. What will it do? It'll factor A once and then do 2 back substitutions, back solves, one with B1 and one with B2. So this is an order n cubed algorithm. Actually, or I should say, quite specifically, it's n cubed plus something n squared. And this would be n cubed plus like 2n squared. What's the difference between these two? They're the same. And you will, in fact, find that. So it's the most ridiculous thing. If someone walks up to you on the street and says, I need you to solve one set of 1,000 variables, 1,000 equations. And they say, you know what, actually, I have 10. 10. Same set of equations, 10 right-hand sides. Please solve it for me. Guess what the time is? Identical. It's cost free. It's zero. It's insignificant. It's the same. So again, this is not obvious, but now you know it, and it has to do with the factor solve method. This will be more clear when we get to actually how this is done. But that's it. These things are just like not if someone tells you that it's to calculate A inverse B1 up to A inverse BK is depending if K is less than if K is less than or less than n, like if it's order less than n, in this case, like if it's 10, then this is the cost is absolutely identical to calculating just one. It's weird. These are not, these are not obvious things, and I think a lot of people don't know them, which is kind of doesn't make any sense. So the cost of multiple solves is one factorization plus m solves. Okay, we'll get to that. We'll see. Okay. Now let's talk about the factorizations. I won't get very far, but I'll say a little bit about it. The most famous factorization actually just comes from Gaussian elimination, and it's this. Any non-singular matrix you can factor into a permutation, a lower triangular, and an upper triangular matrix, period. And in fact, if you want, you can even insist that either the L or the U has ones on the diagonal. So this permutation, this factorization is by no means unique. Nor, by the way, are we going to look at how it's done. If you take the 10-week version of the thing we're going to cover in a lecture and a quarter, actually one lecture and a quarter, you would know all the details of how you actually calculate this. Now the permutation matrix is absolutely required. So I can actually easily make up a matrix A. I shouldn't have said that because I actually can't. If I had to do it right now, I probably would fail. No, I might be able to do it, but I'm not going to try. You can easily make up a matrix A that's non-singular, but which cannot be written as LU. So you may have to permute, in this case, rows or rows to make it so the P here is not an extra thing. Actually, the P, if you take one of these classes on numerical methods, the P is chosen for two things. First of all, there's the mathematical issue that it's just not true that all non-singular matrices have an LU factorization without the P. Number one. Number two, it's chosen so that round-off errors obtained when you calculate these things don't kill you. So that's the real reason that P is used. But okay. Now the cost of that factorization is 2/3 n cubed flops. Okay, so here's how you solve equations, and it's roughly. Actually, it's not roughly. This is sort of what MATLAB does by calling LAPACK codes. I might add. It works like this. You have AX equals B. A is non-singular, so it first carries out a PLU. By the way, this is called an LU factorization. The P is understood. So if someone says it's an LU factorization, they mean PLU. So an LU, you do an LU factorization. That's 2/3 n cubed flops. And then what you do is you start by solving P. You permute the right-hand side. Then you do forward substitution and backward substitution. Each of these costs n squared flops. So this is negligible. Well, except if n is like 6 or 8. But then in that case, these things are different rules come into play when n is 6 or 8. So, but if n is whatever 100 or 50 or more, then it's just order n cubed. So the cost of solving, now you know the following. For dense equations, the cost of solving one set of linear equations is n cubed. As a single data point, my laptop last night, n equals 1,000, half a second. Okay? And the cost of solving 8 sets of linear equations with the same coefficient matrix would be on my laptop what? Yeah, it'd be basically unmeasurably different. It would be, you couldn't measure the difference. It would be the same. And the reason is you do one factorization, and then once you've got the factorization, you do back solves 10 times or something like that. So, okay. So I think we'll quit here and then continue on Thursday. And let me remind you, the section that would have been yesterday is tomorrow.